Hi students, today we are going to learn about a Pythagoras theorem. So the theorem 6.7 says if a perpendicular is drawn from the vertex of the right angle of the right triangle to the hypotenuse, then triangle on both sides of the perpendicular are similar to the whole triangle and to each other. It says that if there is any right triangle, and this is the right angle and the vertex, so we are drawing a perpendicular drawn from the vertex of the right triangle. So this is the vertex of the right triangle at right angle to the hypotenuse. From here I am going to draw one more perpendicular, then the triangle on both sides of the perpendicular. So both the sides you can see a triangle, right? This is the one triangle and this is the another triangle to the perpendicular. You can see the both two triangles are similar. So given the both are similar to the whole triangle and to each other. So this small triangle is similar to this big triangle, and this second small triangle is also big to this big triangle and is also to each other. This two small triangle is also similar to each other. This we can prove by this similarity criterion we already done in the previous exercise. So the proof is left up to you. So next, the theorem 6.8 says the Pythagoras theorem. Here we are going to prove this theorem. In a right angle, we know all this already, this statement. In right triangle, so this Pythagoras theorem is for a right triangle. The square of hypotenuse is equal to sum of square of the other two sides. So here is the hypotenuse. AC square is equal to AB square plus BC square. This is what we have to prove. So here we go for the proof. So the given that we have considered that right triangle ABC and where it is right angled at B, right? Right angled at B. So to prove, we have to prove that AC square is equal to AB square plus BC square, right? The side opposite to right angle is the hypotenuse side. So the hypotenuse side square is equal to sum of square of other two sides. So here we are going to prove with help of this theorem. So this theorem says we are drawing a perpendicular line from the vertices of the right triangle, right? So from like that we are going to construct one perpendicular right from the B. So here will be the right angle, and let me call this point as a D. So this is what we constructed, right? Construction. What here construction? Draw BD perpendicular to AC. Right? Then here we go for the proof. So by this above theorem we can say that the triangle ADB is similar to the triangle ABC, right? So triangle ADB is similar to triangle ABC. This is by theorem 6.7. We already know. So we have to clean with the vertices, right? And A are the common, right, for the both the triangle, and D is right angle and B is right angle. We are choosing the triangle ABD and ABC, right? This and these are the common, and this is a right angle and this is also a right angle. So by AA similar criterion, both the triangles are similar. So while writing this corresponding sides, we have to be very careful. So now why we are taking this sides means we can prove that the AB square from this similar triangle and BC square from the next similar triangle that we have done in already. You remember it, I think. So this will be having an 3 ratios are equal. That is an AD by AB is equal to actually we need first with this we are going to prove that AB and AB, right? So AB we will be taking. So the things involving that alone we can choose. So AB here, the first one is we got an AB and AD, right? So AD by AB, next AB and AC alone we can choose. AB by AC. Actually another one is also there, we don't need to concentrate, DB divided by BC, but we no need this now because from this we can get an AB square, right? So just take an AB here, it will become AB square, and here it will become a AD into AC. AD into AC is equal to AB square. So let it be the equation 1. The same way now we will compare this triangle, this small triangle and this big triangle. So here the vertices C are the common and B is corresponding to D, and C is corresponding, right? So therefore triangle BDC is similar to triangle B is 90 degree, and here it's an A and D is corresponding, this D is corresponding to this angle. A, B and C are the common, right? So these two are similar. So this is similar because of the theorem 6.7, and we can choose the, likewise we will be getting a 3 ratios, the 2 is enough. So previously we have choose for an BC, now we are AB, now we are going to choose for a BC. So for BC is first and last, and here the last two. So first I will choose for these two things, CD by BC is equal to, next first and last, BC by AC. There is another one also, but we no need to concentrate the first two, BD by AB. We no need, because here itself we will get a BC square, right? So if you take here, it will become a BC square, it will become multiplication. So AC into CD is equal to BC square, right? Equation 2. Now let me add 1 and 2. We are adding 1 and 2. So we will be getting an AB square plus BC square is equal to, what is AB square value? AD into AC plus here AC into CD. You can see that AC are common, we are applying a distributive property. So we will be getting an AC into AD plus here is a CD. So from the figure you can see that AD plus DC is equal to full length AC, right? That is what here is also, AD plus CD is equal to AC, right? So AC into AC we will be getting, it is a AC square. So what is here? AB square plus BC square. So this is what we have to prove. Clear? And here we go for the next theorem. In a triangle, if square of one side is equal to sum of square of other two sides, then the angle opposite to first side is the right angle. This is like a converse of the Pythagoras theorem. If we prove the one side of the square is equal to sum of square of other two sides, and which we have chosen the side, the opposite angles will be a right angle. So here we go for the problem. Sides of triangles are given below. Determine which of them are right angles. In case of right angle, write the length of its hypotenuse. So first we have to say whether right angle or not. So to prove right angle or not, we know that the sum of square of two sides will be equal to the square of the hypotenuse side. So and always hypotenuse is the longest side. So let me choose the hypotenuse as a 25. So 25 square is equal to 625, and we have to find the sum of this square is also 625, then it is a right angle. If it is not, then it is not a right angle. So 7 square plus 24 square, 7 square is 49 plus 24 square is 576. So if we add, we got a 625. So hence it is a right angle triangle. The triangle with this three sides forms a right angle triangle, and which is the longest side? 25 is the hypotenuse, right? So therefore given sides makes right angle triangle with hypotenuse 25 centimeter, right? So for the second one, the same, which is the longest here, 3868, right? So 8 square is equal to 64, and the balance you have to square and you have to add. 3 square plus 6 square. 3 square is a 9, 6 square is a 36. So 36 plus 9 is 45, both are not same. Therefore, given is not a right angle triangle. So therefore, the given triangle is not right angled, right? So for always choose the larger number as the bigger number as the hypotenuse. So here we go for the next problem. PQR is a triangle right angled at P and M is the point on QR. So there is a PQR right angled at P. So here all the triangles we are considering as a right angled triangle, and right angled at P, and let it be Q and R, and M is a point on QR. Here let me consider as a point M such that PM is perpendicular to QR. PM is perpendicular to QR, and this will satisfy the theorem 6.7, right? So whenever you see the right angle triangle and right angle at hypotenuse, the 6.7 theorem says that the three triangles also similar to each one. So show that PM square is equal to QM into MR. That's easy, right? So here involves the side PM, 2PM, and another one is a QM and MR. So this small triangle and this small triangle are, they are saying it is a similar, right? So by theorem 6.7 we can say that triangle PMQ is similar to triangle. So we have to check the corresponding sides, and here M is a 90, both the sides are 90, right? These two triangles we are going to put, this is 90 and this is 90, so these two are corresponding. So M will be placed with M, and the Q will be equal to the angle P, this angle, and this will be equal to this angle, right? So therefore triangle R M P. So which two we need? PM, QM. PM we need, and another PM is this pair, right? So first two pair, PM by RM is equal to, next this is the PM, right? So here MQ by MP. So if you take here PM into MP is a PM square is equal to here MQ into RM. This is what we have to prove, right? PM square is equal to QM into RM. MR. That's the before. That's the same, right? So here we go for the next problem. In figure ABD is a triangle right angled at A. So figure is given, it is right angled at A, and AC is a perpendicular to BD. Show that these are all the things we have to show. So I think this each one takes the each similar triangle, right? So the first one AB, BC and BD. So AB contains the both, and one is BC and another one is BD. So this small triangle and this big triangle, right? So for first one, by theorem 6.7, the small triangle and the big triangle, right? Small triangle is the triangle ABC. So triangle ABC is similar to the triangle, the big triangle DBA. DBA, right? So here just consider that the C and A are the 90. So likewise you have to take, and B are the common. So which two we need? AB in the both sides. So this is the AB and this is the AB, right? So AB is the first two. So AB by the first two is a DB, which is equal to last two, right? BC by BA. So if you take here AB into AB is an AB square, which is equal to BC into here go DB. So that is what we have to prove for the first case, and next we will go for the second one. Here you can see AC, both triangle have the AC, and the one other one is BC and DC, right? So this small triangle and this big triangle. By theorem 6.7, you can say that triangle ABC is similar to triangle DAC. CC common, it's 90 degree. So with that we are writing. Then which one we need? AC, right? AC square. So first and last, and here last two. So first and last is an AC divided by here DC is equal to the last two, BC divided by AC. So if you take here, it will become an AC square is equal to BC into DC. That is what we have to prove here. And the next, the third one, AD square. So both AD, it's a BD, big triangle, and CD, and this small one. So triangle BAD will be similar to triangle, then B and B and D will be equal. No, A and C are 90, A, C, and the rest D and D are common for the both triangles. Small triangle and big triangle, D and D are common, right? So which one we need? AD, the last two, and here AD is first and last, right? So last two is AD by CD is equal to the first and last, BD by AD. So AD will become an AD square, which is equal to BD into CD, which is we have to prove. Thank you.